Good afternoon, everyone. My name's Gareth Leonard. As you heard, I'm the Managing Director of Regenesis in Europe. I'm going to talk to you this afternoon for about 20-25 minutes about in situ treatment of PFAS using a colloidal activated carbon. I'm going to briefly talk about the process and then give you a few examples from around the world. I really want to focus on one study from the Middle East that was done by a client of ours where they tried out lots of different techniques, and they really looked into the effects on distribution, pressure of injection, the size of the particle and things. And it's really interesting, and there's a published paper on it. So I linger on that, and then I'll give you the links to where you can get more information. So PFAS, very briefly, we all know the issues in groundwater. You get very large, widespread contamination, and that contamination is low concentration, but even lower targets. So it can be very difficult to treat. There are limited options at the moment, although lots of people are developing them, and there are going to be many different solutions, I'm sure, to this problem. At the moment, a lot of the time when you're looking at treating a plume, you're looking at pump and treat, and then you're filtering on the surface, and then taking that for either destruction, which is being developed, or to landfill. There are in situ destructive techniques being developed, but a lot of those are in lab or pilot scale at the moment. So I want to show you an option for remediation that exists at the moment. This is a product we have called PlumeStop, and it's a colloidal activated carbon. So a lot of you will have heard or dealt with granular activated carbon. So that normally has a diameter of about 1,000 microns, something like that. You might have used powdered activated carbon for the filtration of vapors, for instance, and that will have a diameter of maybe 100 microns, something like that. Colloidal activated carbon, what we've done is we've milled activated carbon down to 1 or 2 micrometers. So that's the size of a red blood cell, that's the size of a microbe. It's incredibly small, and we've suspended it in water using distribution agents to create a colloidal liquid. So it's a true liquid in the way that blood is a liquid, milk is a liquid, wine is a liquid. And what you can do with this product is you can inject it into the subsurface at very low pressure so that you're not creating any fractures. It moves through the formation and it paints the subsurface. And as it paints the subsurface, it turns a contaminated aquifer into a purifying filter. One of the other advantages, apart from the injection of the product and the way it distributes, is because the particles are so small, there is a very short distance from the surface to the internal sorption sites. So it makes sorption of PFAS, the removal of that PFAS from the groundwater, very rapid and very effective. So you can get very rapid treatment that lasts a long time. Just as an example, a visual example to see the product flowing through the subsurface, we've added some colloidal activated carbon on the left and powdered activated carbon on the right. And then we're just putting water on top of that under no pressure, just gravity, and you can see that the colloidal activated carbon works through those pore throats and it paints that silty sand. The powdered activated carbon is clumping together, so although it might be 100 micron, it might even be less, it's clumping together and creating bigger floccules that you simply can't get through those pore throats. So in terms of PFAS and the risks it poses and how we're treating it, the receptors due to a PFAS spill or the groundwater itself, which might be used for drinking water, it might connect with surface waters that could get contaminated. There might be residential properties that it could affect. There might be a legal issue with the contamination moving beyond the site boundary of the person who spilt it. And so what we're looking at doing with this technology is creating a barrier generally at the edge of the site, quite near to the source area, where we're basically cutting off that source from the receptor. We're cutting off the contamination from the receptor using an in situ barrier. So The process is sorption, it's in situ sequestration, it's in situ retardation of the contamination. We're stopping that migration of the contamination through the subsurface. We might, if it's a very large plume, instead of trying to cut off the entire plume, you might cut off the receptor from the plume itself. What we're doing is removing the exposure. We're removing the risk by stopping the exposure of the receptor to that contamination itself, and that removes the environmental risk. This product can be used standalone, so it can be used as a solution to the site. I think as things develop, just like every other contaminant that we come across, generally on a site, multiple technologies are used. So I can see more and more that this technology will be used in conjunction with source treatment, and that might be stabilization, it might be excavation, it might be pump and treat with additives, etc. It might also be linked to destructive technologies as they develop. It's a low-cost solution in that there's no operation and maintenance. You put the product into the ground, it's a passive solution. It will basically filter the contamination out of the groundwater for decades. So years and years, and then really when it eventually becomes saturated, 20, 30 years in the future, you're coming back to site and you're just re-injecting again. And that might be 1 or 2 weeks worth of work on site with a direct push injection rig. So there's actually very little work involved in giving you decades of treatment on the site. So nothing's going to landfill either. There's no cost from waste. So retardation, it's a dynamic process. What you're actually doing is slowing the contamination as it moves through the subsurface, but it's an extreme form. We are slowing this contamination dramatically compared to how it would normally flow through the subsurface. So if we use an example here, we've got a 5-meter barrier with a standard dose. Groundwater's moving at 50 meters per year, and we've got a challenge concentration of 100 micrograms per liter. The groundwater might move through this barrier within 37 days. PFOA might take 57 years, and PFOS, which sorbs even better, may take 200 years. So it's an extreme example in this case, but actually, if a lot of these sites have lower concentrations, and if you look at the isotherms, the way they curve towards the lower concentrations, they actually sorb better at those lower concentrations. So you can get an extremely long period of sorption. Of course, you have to take into account the groundwater flow rate, the level of contamination, and then other things that it will sorb as well. It's not just P4 and PFOS that you might be aiming at. There's all the precursors, there are other contaminants there, etc. But these things can all be added into the model. So the benefits of using this product is that it's a proven technology. We've done 14 sites to date, where we're moving on to the 15th soon. We've got a number of data sets all progressing, the longest of which is 4 years. It's very effective. You get rapid results that last a long time. And it's an available product. PlumeStop was not invented to treat PFAS, and we've used it on hundreds of sites now. So it is a product that we know how to use very well, and so it can be used very rapidly. It's not an experimental product. So an example, some data that we just got back from Michigan in the US, the Grayling Army Airfield. This is one of the largest military bases in the US. As part of the base, they've got an airfield, and in this part, they have a storage area, a tank storage area, where they've got a mixed plume of chlorinated solvents and PFAS. So it's a mostly homogeneous sand. There are some clay layers in there. It's fast groundwater flow. The treatment zone is about 5 to 8 meters below ground level. We've got very low concentrations of PCE, and then we've got about 130 nanograms of PFAS, and they are the sulfonic acids. And there are sensitive receptors nearby. You can see from that drawing that there are residential properties just over the boundary, and there are surface water courses there as well. So this is a pilot study. We injected into the orange diamond shapes. The groundwater is flowing from the top of this drawing to the bottom. It's a slightly curved line, and that's because we weren't quite sure exactly the direction of the groundwater flow. So we want to make sure that we catch it even if it's slightly off from perpendicular. You'll notice that there's some yellow points as well. And what we're doing there is we're coring in between the injection points to try and see where the product has gone, to ensure that we're getting interlocking radius of influence from each of these injection points. What we don't want to do is create a fence where there's gaps where the contamination can flow through. We want to see that we've painted in between those points. And there's a couple of ways of doing it. One is by coring, and if you go from the right to the left on those cores, you can see we work down from the surface, and then we get to the treatment zone where it goes black, and that's actually the colloidal activated carbon that's coated that subsurface. You can then do samples of the cores themselves. You can do this while drilling, etc. And there's a field test kit as well where you're looking at the groundwater, and you can test this by the monitoring wells or go in and test using direct push. And you look at the color of the water, compare it to a standard concentration of plume stop that we have, and you can then see what level of plume stop you've got in the ground, so you can see that you've got the interlocking radius of influence that you need. This graph's a little complicated. On the y-axis, we've got the concentrations of PFAS. On the x-axis, left to right, you've got the time going to 18 months. And then on the z-axis, in the background there, is up gradient. The red line is up gradient of the barrier, and then green lines are wells, or data from wells down gradient of the barrier, and moving further down gradient, the closer it gets to you on the screen. So you can see that the up gradient wells have about 100 to 150 nanograms per liter. The down gradient, you see, we get this rapid reduction in about 30, 40 days. And then that's maintained for 18 months and counting so far, while the concentration coming in remains above 100 nanograms per liter. You can see that further down gradient, they only started monitoring at about 180 days, but you can see on that last line, it's slightly higher and then comes down. And if they'd monitored earlier, what you would have seen is that those levels weren't affected immediately by the treatment, but as the cleaner water comes through and as we work through the back diffusing mass that will leave and attenuate, we then get down to those low concentrations. So we're hoping to go to full scale. It's a little bit slow at the moment because the US is still deciding on what PFAS targets they want to have. And so some of the larger government bodies aren't moving forward with a lot of their PFAS treatment until that is decided. But we're hopeful that this and some other military bases will go ahead soon, maybe depending on the election. Okay, this is a really interesting study that I will go through in the next 10 minutes, hopefully. It's in the Middle East. It was a study done by a remediation contractor from Canada called In Situ Remediation Solutions. They partnered up with a risk assessment consultant called Pole Water Solutions, and they worked on this with the University of Waterloo, Toronto, and Carleton University. And what they wanted to do was look at potential remedial options that have been discussed in literature or tried out in laboratories, such as different sorption materials, such as activated carbon, biochar or charcoal, in ion exchange resin, and then oxidants such as sodium persulfate and hydrogen peroxide. And they want to try that in the field and then test a number of different things, you know, how effective they are, how long they last, how much they're affected by the heterogeneity, what distribution do you get? And the one at the end there is an interesting one, which I'll come on to, which some of you might not have thought of or read about, which is how you affect the filter packing of the wells themselves, the monitoring wells, so that those monitoring wells stay relevant, so that they're actually giving you the correct data. And I will come on to that. So this site is in the Middle East. I can't really say where, but it's one of the largest fuel storage and refinery facilities in the world. They have a very large petroleum hydrocarbon plume. The BTEX on that site is what is driving the risk, fairly low concentrations of that, but it's quite widespread. And then we've got PFAS mixed in there from various incidents and from training on the site as well. They tested for PFAS and found basically 6 perfluorinated carboxylic acids of varying concentrations in there. The geology is sand. It's fairly permeable. There is a thin layer of medium grain sand, which is more permeable and takes some of the flow. It's an unconfined aquifer. Groundwater is about 5 meters below ground level. Permeable, as I say, groundwater flows maybe about 70 meters per year. And it's all slightly reducing conditions, as you might imagine, in the middle of a large BTEX plume. There's been a lot of scouring of the oxygen in the groundwater. So they wanted to pilot test 6 different products to see how effective they were. The first 4 are sorptive materials. So you've got colloidal activated carbon, which is the PlumeStop product that we talked about earlier. We weren't involved in this. We provided the product to this study. Powdered activated carbon, the biochar, so charcoal, ion exchange resin, then we've got then we've got sodium persulfate, then we've got hydrogen peroxide. They chose 10% for each concentration just to reduce the number of variables. This opens a little bit of question as to whether it's the right dose then. So if you look at colloidal activated carbon and powdered activated carbon, 10% is about right. Biochar and ion exchange resin, there's not really enough data to go on for in situ treatment with those products to know whether that's a high or low dose. Sodium persulfate, it's possibly a bit of a low dose there. Hydrogen peroxide, it's probably quite a high dose. The other thing to note is the order there. Colloidal activated carbon is 1 to 2 micron in diameter. Powdered activated carbon is about 100 micron in diameter. The biochar they used was about 200 micron in diameter, and the ion exchange resin was getting on for 700 micron in diameter. So they're quite large particles, except for the colloidal activated carbon. So this is what the each cell looked like. Basically a permeable reactive barrier. Groundwater flow is going from top of the picture to the bottom of the picture. You've got 8 injection points on a 1.5 meter injection spacing. You're monitoring through wells. You've got cores, and then you've got a multi-level well in there as well. The injection zone, the target zone, is 1.5 meters, from 5.5 to 7 meters below ground level, and they're injecting every 0.6 of a meter through that. I'll come on to this, but just point it out now during injection. For 3 of the products, the colloidal activated carbon and the chemical oxidants, they were able to inject with very low back pressure. For the other sorption materials, they had to go to very high concentration pressures, up to 17 bar, which is suggestive of having to fracture that into the formation. So they were monitoring through 50 mil wells and a multi-level pipe on a few of them, not all of the cells. They were measuring benzene, all contaminants, PFAS, general chemistry, and they monitored for 18 months before stopping. They did cores for TOC, persulfate, and hydrogen peroxide, and they measured hydraulic conductivity. Okay, so this graph, the y-axis is depth. Each little graph going along the x-axis is the hydraulic conductivity, and then we've split that up by the product that was used. That line in the middle, just under 6 meters with a hash on it, that's the sandy lens, so that's the most permeable zone. And what we're looking at here is how much the hydraulic conductivity was affected by the injection, and with the colloidal activated carbon and the liquid chemical oxidants, that there is no effect on that. They just flow in, and they haven't affected the hydraulic conductivity at all. With the larger particle size of the other materials, they've had to fracture those in. It looks like most of it has forced its way into this sand lens and start to block that sand lens, so that hydraulic conductivity has been affected by the application. So looking closer at this, looking at the distribution, this time we're looking at the TOC, and we're using TOC to measure where those sorptive materials have gone to. You can see here with the powdered activated carbon that a lot of it, and the biochar, that a lot of it has gone into this high K zone, this medium sand zone, and not a lot of it has gone into the rest of the treatment zone, which granted has a slower flow rate, but will still be carrying quite a lot of contaminant mass and so needs treating. If you look at the colloidal activated carbon, you get much more even distribution right through the target zone. There's no difference in the highly permeable zone. It's not taking all of that mass. So you get much more accuracy of where you're putting the material, and you're getting treatment of the entire contaminated zone. Here we're looking at the filter pack of the well itself. The reason we're doing this is there was a study in the States where powdered activated carbon had been used on petrol filling stations, and those petrol filling stations were found to have great results. But what had happened is the powdered activated carbon had fractured through the formation, filled up the packing of the wells themselves, and turned the wells into filters. So the wells gave you great results, but the subsurface had not been treated. And we can see the same here again. These graphs are a little bit complicated. The red is the level of TOC in the soil. The white squares are what are in the filter pack. And then that line, that ladder on the right just shows you the depth that the filter pack goes to. And you can see for both the powdered activated carbon and the biochar, the level of product has in the well is much higher than the formation itself, so potentially going to give you misleading data. You can see with the colloidal activated carbon over the treatment zone that there's a good correlation between the amount of colloidal activated carbon that went into the formation and that's in the well, and so the well has been treated the same as the subsurface as well, so it can be said to be representative. And hopefully what I've just said there is being said in German. So on to the results. With the chemical oxidation, the hydrogen peroxide wasn't really expected to do much. And sure enough, it didn't do anything in this particular case. I forgot to mention the sodium persulfate was unactivated. This is because the groundwater is 30 degrees Celsius. So it's basically being heat activated anyway, so there's no need for activation. It may have done nothing. It may be that you can see a little bit of treatment there of PFOA, and then maybe it's overcome or it's washed away, or there's too much mass in there for it. But overall, we're not seeing great results from the chemical oxidation of these very recalcitrant, low concentration contaminants. So it's not surprising. I'll speed up because I've only got a couple of minutes left. The sorption results, what we see is all of the sorption materials show a good reduction early on, but then they show rebound straight afterwards, some worse than others. The biochar doesn't work very well. The ion exchange resin lasts the longest, but what you then see is the shorter chain material coming through, followed by the longer chain because of competitive sorption. The colloidal activated carbon, you get this good result early on, and then it stays that way for the 18 months. If we look at this, looking in particular at the high flow zone, we see again that the colloidal activated carbon gets good results and stays low, and the other sorptive materials show breakthrough. Again, the shorter chain material first, and then the longer chain material starts to then break through, probably because they're becoming overcome. They may have created fracture pathways through the formation, or the particle size is just making them inefficient. So here you can see that the colloidal activated carbon distributes well and you get good treatment. The chemical oxidants distribute well but don't treat very well. The other sorptive materials don't inject very well, don't distribute very well. They get an initial result, but then they get rebound, basically. So basically that is in words what I've just gone through on that table. So I'll fast forward through that. There is a paper on this that you can go online and have a look. It's a really interesting paper. It doesn't answer all the questions. It probably poses more than that it answers, but it's an interesting development in our understanding of treatment of PFAS. Further work that's being done, we're working in Sweden with some universities on a site there with some good results. The same group that did that Middle East study are now working on a Bedrock site. You can see we've got one data point there, which is looking good, but it's one data point. We're working with Princeton University there because you've probably read this paper. There's some idea that there may be biological degradation of PFAS. And then we have some commercial sites going ahead, probably one more this year, and then a number next year. Okay, thank you very much.